All right, here's going to be the lecture for Class 19. This is the third installment on the chapter concerning bolts, and we're looking at lapped joint failure. This is an excellent opportunity to introduce concepts regarding trying to do failure analysis and to try to look at the least likely failure that could possibly happen. This class, this lesson or this section here is really kind of closer to being riveted joints, but bolts can be used in this type of application, or we can find areas where bolts get used to resist a shear moment when we have two plates that are connected to each other. We have here in this figure a bunch of different failure modes. So at B right here, what we're showing is bending failure. And you could think of that failure as being due to the forces when you have two plates that are lapped like this are not aligned with each other. And that results in a moment within the plate that causes a bending stress. And that happens pretty quickly. It doesn't take a whole lot for bending failure to take place. It doesn't necessarily mean that you can't have another failure mode once bending failure occurs. Quite often, the forces will be strong enough that they actually kind of get this bend this thing, deform it, and then they get in line with each other, and then the other failure modes can start probably causing other types of failure. And then C here, this is representing shear of the bolt. Right, so this is the type of failure that's very much like this is direct shear right here. This is very much like scissors, right? You can think of the scissors, they're cutting a thing and they're shearing it off. That's what's really taking place inside here. They're like this would be one arm of the scissors, this is the other, and the bolt is in between, and it's shearing across the face, right? So that shear, remember, here's the area, the cross section, and the force is in line, in plane, so that makes it a shear stress. So shear of the bolt and direct shear. D is showing tensile failure of the joint. And of the member, I should say. Right, and we often will refer to the bolt and the member, right? So this is bending failure of the member. I started to write down bolt of the member here. We have shear failure of the bolt, and then we have tensile failure of the member. And you could think of that as being like perforated, because the fact that there are holes here that's taken away material makes this a weak location right here, and so it can rip right along there. We also could have this right here, which is going to be bearing failure. And by bearing failure, they mean like bearing stress, like bearing down, where the bolt is pushing against the hole. And it could either damage the member or it could damage the bolt. So this is either of the bolt or the member. And they will be the equal and opposite stresses, as we'll discuss more. We could also have shear of the, so we have the shear tear out, I guess is what we like to call it, of the member. And we'll talk about that some more, but that's sort of like almost like this little chunk is getting like a sled and getting pushed out, and the shear faces are like right here. And then lastly, we will have tensile tear out, and we don't really calculate that one, but we include it here because the member could like start to rip and start to pull apart right here. So it could be like a normal stress, and it could be the tensile stress, the tensile failure right here. And both of these are really very close to being the same type of failure. Maybe they're just two explanations for the same one, because neither of them really 100% look like this when they happen. I forgot in class to actually bring out some of the specimens. I brought them from class or from my office, and I'll make sure that I make sure that I'll put them in front of the camera here. as we take a look at the different failure modes. But it's a good idea to get like a visual representation of what these things look like. So I have a couple. Now, there's a couple of images that I kind of like, so I included them right here. Sort of like an instance of where you might have other kinds of failures right here. You have to be careful when you take a look at something like here, because we can have failure of this piece, we get a failure of the bolt, or we get a failure of this piece, and they're not necessarily the same thickness right here, or the same material. And you can see here is a good example of the direct shear failure, and you can kind of see that the bolt has sheared right there. And most of the time for failure, we're going to look at permanent deformation. So it's going to be yield, surpassing the yield strength that will happen in this. So here's one that's bending failure. All right, so bending of the member. So in order to find this one, we have to have we get MC over I, right? Well, I just put I don't know why we end up with the I over C on the bottom right here. So we want to figure out first, what is the moment that's going to be placed on this? The best way to do that is to make free body diagrams, and that's going to be true for all of these. If you don't know exactly what's taking place, then don't just trust equations. Make a free body diagram. All right, so here's part of the bolt in this joint. So what I've done is I've taken this right here, and we could even put the head back in there if we want to. And we put this, we have this load placed onto this. So let's draw that load in place. And the load is centered. Let's say that it's centered somehow on the plate. Now, there's also going to be a load from the other plate pushing back on this bolt, right? If we were to take a free body diagram, if we're going to take the sum of the moments and take it about a point right here, right, we would need to have a resisting moment that's placed this way, right? Because the force right here is trying to go clockwise, counterclockwise if we're taking it about here. So we need to have a moment to balance that out that's going clockwise, right? So that right there is going to impart a bending stress right here onto this piece, or really probably closer to like right in there, and that's where we're going to see the bending. And the C is really okay. So we could just look at the plate and focus in on the plate, and it's got the moment is being placed right about that right here. Well, the C is going to be from the neutral axis to the outside fiber, and the I is going to be the cross-sectional properties, right? But you're going to subtract out the BH cubed over 12, right, where this is going to be the H of the cross-section, and the B is the base of the whole thing, but you have to also subtract out the missing spot that would be right here for the whole, and you end up with the bending stress. And this is the kind of stress, this is normal stress, so you would use the shear stress, shear strength, not shear strength, excuse me, the yield strength. Take that back. It's the yield strength because it's a normal strength. So you want to, every one of these is going to be a safety factor that's going to be based on the strength and the stress that's appropriate for the situation here. So that's going to be whatever, the MC over I of this thing, right? There's the strength over the stress. I'd also point out sometimes they also try to look at the bolt right there, and they could say that the same moment is being placed onto the bolt, and it too is being bent. But I really kind of think of that as being needing to have sort of a gap in there, because the bolt is going to kind of remain relatively straight. Saying there's a bending moment on it, I don't know. I find it a little bit difficult to buy, but I guess maybe if you were to take a look at this and put the force right here, and you were to hold this as a steady right here, I guess there would be a bending moment on that. So I guess the bolt could bend, but it just seems to me that there's not enough like room, that you actually need like some kind of physical gap to be placed on there. Anything else I want to discuss in here? I think that's it. All right, so this guy seems to be out of place right here. Yeah, I should move this slide. So I'll discard that thing that I previously wrote up on there. And I think this guy needs to come down to right here. While I'm still on this bending, let me take a look. Let me show you, and I'm out of this. Let me, because my laptop is closed, I got to use this little thing here that's kind of silly. All right, the camera. It's going to do that. Okay, I'll turn the camera on. And you can see this wonderful skull diagram here up above. And let's see. Okay, so this is a riveted joint right here, and it still applies. And you can see when it was in this tensile test right here, it bent almost immediately. So there, right there, that's the bending failure that you would expect in bending. So let's see. We'll go back to this, and we'll go on to our next slide, and that's going to be our shearing, right? So these are the bolts in shear, and once again, we got to be careful not to plug and chug in as part of these. It's going to be F over A, but the A is going to be dependent on the number of bolts as well, right? So it's the cross-sectional area, right, that we want to find. And even though, truth be told, that shear wouldn't be evenly distributed across the bolt, this is an approximation or a model, right? That we kind of almost know that we look at that. It's probably going to be shearing probably more in the center than over to the side. And if we remember from transverse shear, we did have a distribution. But the distribution and direct shear, when these loads get really closer to each other, closer to the supports, is kind of like the idea. We go ahead and make the approximation that it's evenly distributed across the entire face, even though that's not true. And then, so that's the shear area, and we also want to know that's the number of bolts too. And we want to be careful here that when we make a comparison and a safety factor, that we use the shear yield strength divided by the shear stress, the tau. And remember that the shear yield is equal to 0.577 times the normal stress yield strength. Remember that came from von Mises stress, where we had sigma squared plus 3 tau squared. This is just uniaxial plane stress. And that if we had zero normal stress right here, that we would end up, and we would replace this with the shear strength right here onto the thing that I guess maybe we would take the yield and set it to that. We would have the square root of 3 times tau squared, so that the yield strength of this thing would be the square root of 3, 1 over the square root of 3, to be able to get the equivalent shear yield strength. And if we were to have this kind of situation, this is like the one that the equations are for in the book, but we could definitely double up the plate right here. And if we wanted to figure out what kind of area to use, we would need to do free body diagrams here and remove the plate so you could look at the bolt. This is often what's necessary if you're unsure about which area to use. Draw these little tiny figures and figure out how that's going to happen right here. And you can see that separating out these little parts right here, that what we're going to find is that for a particular location right here, that we're going to have 1/2 of the force is going to be loaded on top of this piece, and 1/2 is going to be on the bottom, as opposed to over here where it's the full amount of the force. And if there's a number of bolts, then you're also we would double it. If there was 2 bolts, we would double it up. So there could so that's the approach we need to take. We need to be thinking in those terms all the time. And so a shear failure, we actually have that here. Let's see. All right, so this is a shear failure right in here. Right, so you can see that the rivets right there, there's the heads or the bottom of the rivets, and then you can see that this sheared right off, right? That it just cut the bolt, or cut the rivet right apart right there, and they slid away from each other, right? That's the sliding action, is the shear of the bolt. And okay, so we go on to the next. Here is one that's the tensile failure of the bolt. That's going to be, we can think of this as the perforated one, right? Because there's a hole there, there's not as much meat. So the area is going to be this width minus this diameter, right, times this thickness. It's really going to be this length right here and here times the thickness to be able to get that area. We could also apply stress concentration, but we usually don't. And so for this, the area is simply going to be W times D, minus D times T. And we might even want to extend this and say that the area is going to be the width minus N, which is the number of bolts times the diameter times the thickness. Because like up in here, you could see that there's 2 bolts, so that we would take this, and this, right? So in this case, the area would be the width minus 2 times the diameter, and then times the thickness to get that area. And it's the force is perpendicular to the area, so therefore it's a normal stress. And we want to compare this one to the member's yield strength, right? That's another important thing to point out here. This right here, we would compare to the member's yield strength right here. We would compare this to the, excuse me, I'm pointing to the wrong thing. If we were to look at the stress in the bolt due to bending, we would look at the bolt's yield strength. Here we would look at the bolt's shear yield strength, and here we would look at the member's regular yield strength. Here we have bearing failure of the bolt, and we can think of this as being sort of the area here being the projected area. We actually know in like if we were to do a close-up and exaggerate the clearance between the bolt, so this is the cross section of the bolt, and maybe this is the member that I'm showing right here. Right, so there's here's the member right there. That it's actually going to be touching at one point before it starts to deform, and we know from contact stress that it's going to flatten out, or they're going to get in more of an area is going to get in touch with each other. But we make an assumption instead of having this localized stress that we're going to push across this entire width of this thing, and that it's going to be projected as a like rectangular or a square right here. That's going to be with the area of D, the diameter of the bolt, times T, the thickness of the plate. And that stress is going to be both on the bolt and on the plate, and it could be on 2 different plates, right? So we could have a situation where we have a bolt right here, and there's going to be this right here could have a different thickness than this. So there's going to be a bearing stress in between the, let's see if I draw it in the right spot. It's going to be right here, right? If you're pulling right here, this is the part of contact. So that's going to have a particular stress, and it's going to, the bolt is going to experience it, and the member is going to experience that stress. And then you'll have another one down here because you're pulling this way right here. And there's going to be, if there's a different thickness here between the plates, there's going to be a separate one, but it's going to be experienced by both. Again, the bolt and the member are going to experience that same stress. So you get to find the stress, and then you have to make sure that you're using the correct strengths to make that comparison. And you could think of this as actually trying to lengthen the hole. I think that's the way that I best understand it. They show it as like these little wrinkles or something going on here. But you can think of it as like trying to make the hole bigger, or trying to put a dent into the side of the hole. Now the hole used to be a circle. Now it's a little bit more of an oval, right? And then the bolt, it used to have a nice clean face, but maybe we've put an indentation onto it, right? Here we've taken it and moved it out of shape. We get so here's where they're showing that the hole has elongated here for bearing failure. And then this last one, this is I guess it is the last one, is sort of a weird one. We could use this, but we generally use this as our means, and we take an X, or this dimension X, and I've drawn it a little wrong here. It should actually be like right to there, and then take the area. And we also have a partner one over here that we can't quite see. So let me put it in yellow. We can't quite see. He's behind right over there. And you could think of this as being a sled, maybe a little chunk of metal that's being driven out, right? And it's now this is, you got to look closely at Shigley, and we'll see it's actually to the edge right there. And here is the area, right? And then it's got a partner that's on the back side that you can't see from this view, right? There's another partner right here. So that's why it's going to be 2 times x times the thickness. Let's get him back. So 2, because there's 1, 2, and then x is a dimension, and it's really how close you are to the edge, from the edge of the bolt to the edge of the piece right here, and then times the thickness. And the way to avoid this failure is to move the bolt away from the edge, right? So we make x large enough, 1.5 times the diameter, and that usually goes ahead and takes care of this kind of shear stress. But we should take a look at it and see if it's going to fail. And so let's see a couple of different failure modes that I didn't bother to show right here. I think this guy right here, I have really 2 examples of him. I'll discard it, why not? So right in here, you can see that's definitely a tensile failure right there. There's a lot of material missing because of these holes. The holes are pretty big, so it makes what's left of it weak. Right, so it was weak right here, and it was definitely weak right there. So that's the part that left. And also on this other joint right here, we could also see that this it failed also in tensile failure. So that's a pretty common one, especially if you put too many bolts and the bolts too close to each other. It just makes a great place for it just to rip apart. And I don't have any of the other failure modes, unfortunately, but those are good ones to have to understand. Here's another joint failure. This is a tear out right here. They're showing, and this way, I think you could say that this was the shear areas were going to be right in there. I didn't mean to write in this view. Okay, the shear areas are going to be right in there. Okay, red's good enough. Yeah, right in here. This is the shear area of these pieces falling apart. This is just from another resource where they're saying a good rule of thumb right there. And it's also good to say the center to center between 2 bolts to try to keep it like between 3 diameters away from each other. And here's an FEA that I did where this is actually a little difficult. You have to be careful with your boundary conditions to be able to get and simulate this right here. And it's a little on the It's a little deceptive, but you can see that the holes are getting bigger. Now, of course, this has a scale of 1,000 taking place, so I've multiplied the deformation by 1,000. Just so you could see it, you could highlight it, and you could also put the von Mises stress on there. So you can kind of see that it's got some bending going on. I think that bending, once again, would probably be more pronounced if, or the bending is influenced by the fact that I forced the head of the bolt to be in horizontal. But I kind of had to do that in order for the thing to solve. It likes to crash if you don't have the right boundary conditions on it. And here was another instance where I grabbed a hold of some of those as well. And here's where I put it really close to the edge because I wanted to get that deformation. So one of the problems of trying to actually get these stresses is that they're all kind of really happening at the same time. So it's actually a combined stress type of problem. And here's 2 right in a row. I should have mentioned back over here, one way to stop this from happening is if we have like 2 plates and lapped, is to put 2 rows of stress and then you won't have that condition, or you're really very unlikely to have rip out through the air because it has to also pass through this right here. So if you can double up, that's one way to avoid this condition. Just like other ways to avoid the conditions, if you had for the bending, right here, we can avoid the bending by doubling up on the plate like this right here. And as we'll see in one of the examples right here, we have we could use these backing plates on there. So this is the end of the lecture, and I will make the examples something separate. So thank you.